At the far end of our close group of planets, beyond the orbit of Neptune, something surprising is happening. A disturbing force pushes around cold objects, and groups of these objects have unusual orbits that cannot be explained by known planets alone. Scientists believe this could be due to a large hidden planet, often called Planet 9. This possible new planet was first proposed in 2016 and has intrigued astronomers. Oddly enough, this is not the first time that the planet has been suggested to use mathematics. Neptune and Pluto were both discovered because their gravitational effects were predicted before they were seen through a telescope. Astronomers saw anomalies in the orbit of Uranus and later in Kuiper Belt objects, which led to the discovery of these distant worlds. A century later, we find ourselves in a similar situation with Planet 9, following the fascinating tradition of using numerical predictions to reveal hidden planets. Some studies suggest that Planet May 9 have been a rogue planet captured by our Sun's gravity, while others suggest that it may have formed from the same disk of gas and dust as the other planets. If Planet 9 exists, it is thought to be 10 times more massive than Earth and orbits the Sun at a distance of 400 to 800 Australian dollars, which is 400 to 800 times the distance between Earth and the Sun. Astronomers eagerly hunted for clues, using powerful telescopes and sophisticated computer models to track its effects. After years of looking at the sky, solving numerical equations and sophisticated software analyses, they now have the strongest evidence yet that Planet 9 really exists. This discovery brings an exciting twist to the story of the secret planet. What evidence did analysts find while tracking Planet 9? If we have found exoplanets many trillions of kilometers away, why has it been so difficult to detect Planet 9 directly in our solar system, even with the most remarkable telescopes at our disposal? Although Planet 9 was first proposed in 2016, its story began shortly after the discovery of Uranus in 1781. Over the years, astronomers noticed something strange. Uranus wasn't moving exactly as their calculations predicted. It appeared to speed up and slow down in orbit, indicating that it may be affected by an unseen force. In the 1840s, two mathematicians, Urbain Leverrier in France and John Couch-Adams in Britain, independently proposed that the unusual movements of Uranus might be due to the gravitational pull of a hidden planet. They used complex mathematics to predict where this invisible planet could be found. It was a bold hypothesis based only on mathematical calculations that suggested the existence of an unknown world. Leverrier sent his predictions to Johann Gottfried Galle, an astronomer at the Berlin Observatory. In the evening of September 23, 1846, Galle and his assistant directed their telescope to the part of the sky indicated by Leverrier. Surprisingly, they found Neptune on their first memorable night of searching. This was an amazing achievement because it was the first time that a planet had been discovered by mathematical prediction rather than by chance observation. After the successful discovery of Neptune in 1846, astronomers thought they had a complete picture of the most important planets in our solar system. However, when they traced the orbit of Neptune, they found that, like Uranus before it, it showed small deviations, as expected. These deviations were subtle but consistent. Considering the use of gravitational forces to predict the existence of Neptune based on the orbit of Uranus, astronomers wondered if a similar method could reveal another much more distant planet. This led to the discovery of Pluto. More than 80 years later, on February 18, 1930, a young astronomer at the Lowell Observatory, Clyde Tombaugh, detected a faint distant object moving against the background of the stars, confirming the existence of another celestial body. Originally named the long-sought Planet X, Pluto was later found to be much smaller than expected. The mass of Pluto was not enough to explain the gravitational disturbances observed in the orbits of Uranus and Neptune. This meant that something larger than Pluto was beyond Neptune's orbit that had not yet been discovered. In 1951, Dutch-American astronomer Gerard Kuiper predicted that there might be not one but several icy objects beyond Neptune's orbit, and that Pluto was just part of a larger belt of objects known as the Kuiper Belt. The first direct observations of Kuiper Belt objects, KBOs, were made in 1992, when astronomers David Jewett and Jane Liu discovered 1992 QB1, a small icy body beyond Neptune. This discovery confirmed the existence of a population of objects in the Kuiper Belt, as Kuiper had predicted. As more objects were discovered beyond Neptune, the term transneptunian objects, TNOs, was coined to include all objects orbiting beyond Neptune. TNOs are a broader category that includes all small solar systems that orbit the Sun at an average distance greater than 30 Australian dollars from Neptune or more. The discovery of Sedna in 2003 increased this interest. Sedna, another large TNO with a highly elliptical orbit, is about 76 Australian dollars at perihelion, closest to the Sun, and about 936 Australian dollars at aphelion, farthest from the Sun. In the following years, more distant trans-Neptunian objects were discovered. There is a surprising thing about the orbits of TNOs. Imagine scattering mini marbles on a flat surface. Normally, the marbles should be scattered randomly, but when mini marbles are strangely clustered in one particular area, it suggests that some force or factor brings them together. This scenario mirrors what researchers have observed for TNOs. Their orbits are not randomly scattered, but appear to be clustered. Of course, if TNOs happen to be orbiting, their paths around the Sun will spread out in all directions, just like the marbles in our analogy. Their perihelion points would be scattered across the sky rather than clustered or concentrated in one area. However, their aphelion points are almost always concentrated in some part of the sky. This grouping is very unusual and suggests that their orbits are influenced by a common factor. Moreover, the long axes of their orbits, the lines connecting their points closest to and farthest from the Sun, were aligned in a way that is statistically unlikely to happen by chance. This alignment further supports the idea that an external force, perhaps the gravitational pull of a large hidden planet, shapes the consistent orientation of these orbits. Based on the discoveries of Sedna, 2012 VP-113, and other TNOs, the hypothesis of a distant, unseen Planet 9 is gaining considerable momentum. In January 2016, astronomers Konstantin Batygin and Mike Brown published a groundbreaking paper that further strengthened that hypothesis. They analyzed the orbits of 6 distant TNOs and proposed that these patterns could be explained by the gravitational influence of a previously unknown planet. They proposed that this hypothetical Planet 9 would be approximately 10 times the mass of Earth and would orbit the Sun in a highly elliptical orbit varying in length from 400 to 800 AU. When Neptune was discovered, it was very fast. Astronomers found it on the first night of their search based on numerical predictions. However, the hunt for Planet 9 proved to be much more difficult. There are 4 main questions.
The first is its distance. Planet 9 is thought to be 10 to 20 times farther from Earth than Pluto. At such a great distance, the planet would receive very little sunlight, making it almost invisible against the stellar background and difficult to see with modern telescopes. Another problem is that Planet 9's orbit is likely to be highly elliptical. This means that it can spend most of its time in the most distant and darkest regions of its orbit, away from the illumination of the Sun. If it is at these farthest points, the planet would be even dimmer and harder to detect. The third question is the large area of the sky where Planet 9 could be located. This wide search area requires astronomers to carefully scan large areas, checking observations frequently to make sure nothing is missed. Finally, the planet's slow motion across the sky makes detection difficult. Because Planet 9 is so far from the Sun, it moves slowly relative to the background stars. This slow motion means that identifying it from background stars requires long and repeated observations. Because of these challenges, simulations become an important tool in the search for Planet 9. Simulations allow researchers to model complex systems and predict behavior that is difficult or observable directly. Let's see how scientists use simulations to get the strongest factual evidence for Planet 9. The orbits of TNOs are not stable for a long time, on the order of millions of years. Neptune's strong pull can change their orbits, separate them widely, or even drive them out of the planetary group altogether. This dynamic indicates that TNOs are constantly being shuffled into orbits that cross Neptune. To investigate this more precisely, the research team created simulations based on the assumptions of the formation of the Oort cloud. The Oort cloud is thought to be a spherical shell of icy bodies surrounding the solar system, extending from about 2,000 to 100,000 Australian dollars from the Sun. They selected TNOs with perihelions greater than 30 Australian dollars and semi-major axes between 100 and 5,000 Australian dollars, resulting in a simulation of 10,000 particles. The research team ran two sets of simulations, one with the predicted location of Planet 9 and one without Planet 9. The results showed that Planet 9 can influence the orbits of TNOs through direct coupling of the angular momentum. This vector describes the shape and direction of the orbit under the influence of a force like gravity. Its direction determines the direction of the orbit, and its size is directly related to the eccentricity of the orbit. Zero momentum corresponds to a circular orbit, while non-zero values indicate elliptical orbits. Planet 9 can lengthen those orbits and change their inclination. Simulations showed that without Planet 9, fewer TNOs would come close to Neptune. Notably, without Planet 9 near Neptune, the number of TNOs near Neptune decreases sharply with decreasing distance from the Sun, peaking at about $30. On the other hand, for Planet 9, close approaches occur more consistently at greater distances, starting at about $16. To confirm these findings, the team performed a statistical analysis comparing the patterns observed in the simulations with the real data. They looked at observational biases and matched the simulation results to known TNOs with perihelions less than 30 and semi-major axes greater than 100. The analysis strongly supported a model that included Planet 9, showing a much higher probability of 0.41 compared to the model with only 0.34. Without Planet 9, this significant difference in probabilities indicates that the Planet 9 model more closely matches the observed behavior of TNOs, suggesting that Planet 9 plays an important role in shaping their orbits in the next few years. The Vera C. Rubin Observatory in Chile will start operating, equipped with a powerful 8.4-meter telescope capable of surveying the entire sky at night. This observatory will benefit from the results of recent studies, including those that suggest the existence of Planet 9, by closely monitoring the movements of distant TNOs. If these TNOs consistently have a pattern of proximity to the Sun greater than $16, as predicted by the Planet 9 model, this could be a significant indicator of the presence of a rogue planet. This combination of cutting-edge technology and groundbreaking research could greatly expand our understanding of the outer reaches of our solar system and could eventually lead to the long-awaited confirmation of Planet 9. The James Webb Space Telescope recently measured how fast the universe is expanding. The results confirmed the biggest crisis in cosmology, showing that there is a major flaw in our currently accepted model of the universe. If you missed this part, be sure to follow the exciting discovery. And if you learned something new from this text, don't forget to like it and subscribe to our channel for more news. See you in the next one.